This is a lesson on the big ideas of state functions and conservation laws in a unit on work and energy. In general physics, there are four fundamental concepts that you'll get through: kinematics, Newton's laws, momentum, and work and energy. So, up until this point, you should have a solid foundation in kinematics and in Newton's laws to move forward with the unit for work and energy. And we've looked at both translational and rotational topics in kinematics and Newton's laws. We'll see that as we move forward. And things that you should be familiar with as prerequisite material. Expect this stuff to come along as we move forward into more topics because it is the fundamental material. Definitions, symbolic representations, graphical representations, vector representations, Newtonian's laws of motion. We'll keep those in our back pocket as we move forward in case we need them. And the idea of force. Force is going to stay a fundamental concept as we move forward. And also the concept of the system of objects. We touched on this first in Newton's third law, where we had interacting objects and the rule of action-reaction. Well, most of the world is a system of objects, and we won't get away with it. And how to deal with this, we will keep moving forward with, and watch out for how do we deal with a system of objects. Conservation laws are fundamental, basic, like these are the driving principles in physics, in the cosmos. There's a number of cosmological quantities that are conserved or remain the same through an event. And so energy is one of those. And you will learn on this as we move forward in work and energy. Momentum, both linear and angular, which we will cover, are conserved. Mass is generally conserved as long as there's not a transition between mass and energy. Charge is conserved. These are fundamental quantities in the cosmos that we as physicists can trust will be conserved and which will drive our calculations and how we conceptualize and formalize what's around us. What happens is it's efficient mathematics simply knowing the initial state and a final state. There's things that happen in between, but it's so efficient just to look at initial and final and go from there. So that's the utility of state functions. A state function is a picture of a system at a point. Quantities going on there will be conserved somehow at another state in time. And this is advantageous because it allows us to focus the analysis on the initial and final state only. And this is true for scalar quantities such as energy. You'll find that energy is a scalar, but also vector quantities. Momentum we'll see is conserved from one point to another. And we're just looking at initial and final states. We do not have to get bogged down with all the little details of the analysis of that object as it moves from that initial to final state. That is the opposite of what we want to do. We want to not worry about that stuff and only look at the initial and final state. So sketches and diagrams here I found are very important for problem solving because we need to concretely identify the initial state and what's going on in the initial state, and the final state and what's going on in the final state. So initial and final pictures, and you're used to representations, drawing a sketch, drawing a diagram, etc. So what I've chosen is some different examples that will allow us to look at two different points, and you'll get used to doing this, and I'm setting this up so as we move through the problems it becomes more of a conscious thought for you. What is the initial, what is the final, before you even start getting into the details of solving the problem, just conceptualizing what's going on at those 2 points in time from basic information given in problem statements. So, for instance, we're going to work on the Kerry Pulls the sled problem. You can see that Kerry's pulling a sled along a snowy horizontal path. So we have a horizontal path, okay. And Kerry's applying a force directed at an angle above the ground. So this is a pretty simple situation. I can think of a sled on the ground, right? And in the initial state, it may have some velocity. Kerry pulls on it with some force of a pull, and it moves a displacement along the horizontal ground, some distance d, to some final state. And at that final state, I'm going to say it probably has a final velocity, initial velocity. Okay, so I'm thinking, where did it start? Where did it end? What is its motion at those 2 points? She could have pulled it 50 miles, right? We didn't even consider how far, but we're considering what some quantities are at this point and that point. Here we have a 73 kilogram person in an elevator is accelerating upward from rest to a speed. So I'm seeing a couple of values in here, rest and a final speed. So we have an initial speed and a final speed. Those are things important to note in the problem statement. Over a distance of 8 meters, so it's definitely moved. So we're in an elevator. We have a person. I'm going to keep drawing free body diagrams of objects of interest. So here we're looking at the mass of the person. So I'm just going to draw the person. Here's a person. I assume there's some normal force from the elevator, and of course there's a weight. The person will have a weight, and it moves upward. And I guess what I might do in this situation is have a V initial down here equals 0, right? And I'm measuring, so I will set a coordinate system so that I know y initial equals 0, and then it moves up to y final equals 8 meters, and it has some V final, 2.33 meters per second. And so I'm thinking about the 2 states here, the initial and final. Notice I didn't do anything with acceleration. I didn't set up any Newton's laws. I'm not worried about that stuff. I'm not looking at the particulars of the object yet. I'm just looking at an initial and final state. Here's a skier. The skier coasts up a snow-covered hill that makes an angle of 25 degrees with the horizontal. Okay, so we have a nice gentle slope here. Here's a nice gentle slope, 25 degrees. I'll put that in the picture. Here's the horizontal. The initial speed of the skier is 6.6 meters. After coasting 1.9 meters up the slope, the skier has a speed of 4.4 meters per second. So we can put the skier down here to begin with. There's a skier. V initial equals 6.6 meters per second. After, and you may put like a displacement in here is 1.9 meters up the incline with the V final equal to 4.4. We can see the skier is slowing down. I've labeled an initial and final position, so that's clear on my picture. And if I needed to do a free body diagram of the skier, I could do it over to the side, right? Like if I needed to, okay? So there's the skier example. Here's an interesting one. This is called an Atwood machine. And it's a pulley with a mass system to lift or move different blocks, masses in a gravitational field. So it says 2 blocks are connected over a frictionless, massless pulley. We'll see that those things are important when we get to torque. But for now, we're going to assume the simplest situation. The string is massless and doesn't contribute, etc. So we have 2 masses, a 3 and a 7. So here's the 3 kilogram and the 7 kilogram, and it seems like the system will naturally want to rotate clockwise around that pulley. And so we're going to have some movement downward for the 7 kilogram block and some movement upward for the 3 kilogram block. So I'm looking at initials and finals. So the initial state, I'll have like V1 initial and V2 initial. I need to designate my system of objects, right? We have a system of objects. So there's the initial. And on this one, and you see later when we work on this problem in another lecture, here's the final state. I'll just draw it in there. V2 final equals, and then this block moves up, so I have to watch out for that. This block moves down, that block moves up. So it ends up here, and it has a V1 final equals. And so that's how I'm designating. You could draw a whole nother picture over here, and I'm completely fine if you do that. especially if there's a lot of things going on, a lot of information you need to organize. As much picture as you need, I think err on more rather than less, because the pictures help organize the information, they help encode the problem, help you apply the concepts. And so as much picture as you need is fine with me. So that's the initial and final state for the Atwood machine. I picked this picture out because you can see that as along, it looks like some sledding people. They go down a hill and then they go up another hill, and then it looks like there's some friction down here between D and E. And you can see that we may have multiple final points, right? Of course, they start up on the hill, and I can note that. There's the initial position. But we could have the final at B, we could have a final at C, we could have a final anywhere along this point. That's true. So how do we deal with this? How do you deal with this? Let me see. Is there anything in here that I need to mention as we move? Well, I can look back if I need to. So it may be that you need to find some sort of information at B. So makes sense to go from your initial to your final from A to B. That makes sense. If you know information at A, go to B. Well, then what if you make C the final? What's the best way to do that? And what I found through the years is the student's first instinct, which isn't a terrible one, you're not wrong, is to go from B to C. I do not recommend this. If anything you calculate from B and you're using it to calculate C, you're going to get C wrong. Okay, so watch out for that. That's a propagation of error that you do not want to take on. Also, typically what's going on at A is pretty simple. They're just sitting there. We just have some 50 meters to take into account. That's easy. So my recommendation is not to go from B to C, but to go from A to C. And you may see that, you may already guess that if you're going to know what's going on at D, I would go from A to D. If you want to know what's going on at E, I would go from A to E. I don't think there's any reason to complicate your calculations to introduce a possible propagation of error through your entire problem. And remember, these initial and final states, that's all we care about. And if we're conserving quantities from one to the other, from A to B is equivalent from A to C. Whatever you started out with went from A to B, and then it went from B to C. Well, get B out of the middle. Just go from A to C. And so keep these options in mind as you're solving problems. Just like when we were working with systems of objects and we could choose multiple free body diagrams, here you can get clever with which initial state and which final state you choose.